Now let's talk about how to design um, gain boosting amplifier for stability. First one is stability, right? Any loop should be stable. And second one is fast settling, considering future utilization for switched capacitor circuit. So let's first assume that main amplifier, which is cascode, has a frequency response like this one. So the dominant pole is determined by as you know, the output impedance or resistance, output resistance and the load capacitor. Um, but let me see. Okay, in this case, we are not, nice. Okay, yeah. So the output pole frequency here will be determined by the cascode. So let's say this is the one. And the unity gain frequency of this cascode is just, as we know, GM and CL. It's going to be determined by that, right? GM V in goes through at high frequency L and then it becomes unity. So that is omega 5. And a boosting amplifier has a gain, as shown here, a boost. And the dominant pole is, let's assume that it is single stage amplifier. We usually use that. Its dominant pole is there, and this amplifier's unity gain frequency is here. Okay, let's first begin with that. And then when we make a feedback loop, gain boosting feedback loop, then what happens? Does GM change? GM doesn't change, right? Well, whatever it is, anyway, the current appearing here will be GMV in. So GM is not changing, which means unity gain frequency is not changing. So unity gain frequency is still there. What happens is, as we studied, gain boosting makes the output impedance higher. So with the same unity gain frequency, output impedance increases. So what that implies is gain increase with the same slope, right? So it's going to be like this. So due to a boost, the entire gain is increased from here to here. It's going to be a boost, right? A original is in log scale, it's added with a boost, because output impedance or output resistance is increased as much. Okay, so this red one is this amplifier's rough frequency response. And well, if we are using this amplifier in a feedback network, then for stability, we will check this one, right? But let's not talk about it at this moment. So before we apply feedback, what we're gonna think is um, first stability, and another is this gain characteristic. So if we think a boost gain, I mean a boost is not like this, but like say like this, lower bandwidth. Then what's gonna be the frequency response? From this point, I mean, we have DC gain is the same, but from this point, gain will drop. And then here, when the amplifier gain becomes unity, we have just a cascade because we don't have boosting effect. So when the amplifier's bandwidth is this narrow, then entire gain response will be like this, which we don't want to have. So at least in order to have boosting effect, this one, unity gain frequency should be wider than the main amplifier's dominant pole frequency. That's one requirement. Another is this is about the gain, one pole drop gain, right? That is one thing. So one pole drop is requirement. And another one is stability, right? In order for this loop to be stable, this amplifier's unity gain frequency, should be earlier than the non-dominant pole frequency. Right? Non-dominant pole frequency should be higher than the unit gain frequency for stability. So non-dominant pole of this loop is this node. This is dominant pole node. So this one is actually the non-dominant pole of the main cascade amplifier, which is this one. So unit gain frequency is what? Omega 4. So omega 4 should be lower than omega 6. So two conditions are there, right? First order roll-off, one pole drop, and stability. In continuous time amplifier design, this will be a good condition. But for transient, switched capacitor amplifier's case, we need to consider more. So let's take a little bit more about the amplifier. So if we draw output resistance or impedance, actually, because it's a frequency dependent value, right? So this is the load capacitor of the amplifier, and except for the load capacitor, we have still the impedance of the amplifier itself. So if you see the amplifier itself impedance, then at the DC level, we know cascade impedance boosted by the amplifier, right? So that is that amount. And then when a boost drops its gain, because the loop gain reduces, impedance boosting effect will also reduce like this. And then when this one's gain becomes unity at omega 4, we have only cascade impedance like this. That's this amplifier's output impedance. And this amplifier drives the load here. And load has a frequency response like this, right? Load impedance reduces as frequency increases. So that's seen from the entire output is a parallel of Z out and the ZL. So if we do the parallel calculation, it's going to be like this. They become similar gain, and they were similar gain because they drop together. But when the amplifier output stays there, the capacitor still drops. The impedance of capacitor still drops. So we have this. Well, we discussed the one we discussed, pole zero doublet. So pole zero doublet appears. So what? When the amplifier is utilized with field effector beta, and let's assume that our 1 beta line is here, just like this one. Then this is what? This determines the time constant, which we utilized loop gain unity, omega LU, right? 1 over omega LU is tau, and tau determines settling speed. So this is the major settling component, but when the pole zero W is lower than the unity loop gain frequency, we saw that there is a slow component whose time constant is determined by the pole zero doublet's frequency, right? So that issue occurs when we design gain boosting amplifier. So what's our design guideline? Well, you need to put your pole zero doublet frequency, which is unity gain frequency of your boosting loop. Your gain boosting loop's unity gain frequency shouldn't be located lower than your total amplifier's unity loop gain frequency. So if your amplifier works like this, then that's going to be not good. That's not good for fast settling, because desired settling time constant, unwanted one there. So this one should be higher than that, than the unity gain frequency. So the design requirement now becomes like this. For stability, still the same, right? Unity gain frequency should be lower than the non-dominant pole. For fast settling, doublet frequency should be higher than the unity loop gain frequency. Like if your 1 beta line, is here, if your Um, if your one of beta line is here, then that's okay, because this will be your settling time, right? This is a higher frequency. So last time I got one question, even though the settling frequency is determined by the pole frequency of the pole zero doublet, why do we still be affected by the zero frequency? So I couldn't answer to that, but yeah, sorry about that. But if you see the equation, I missed this point. So I mean, time constant is still determined by the pole frequency of the pole zero doublet. This is unwanted settling time component. This is desired settling time component determined by this one. And this one is determined by pole zero doublet. So this one's magnitude, amplitude, can I say magnitude or amplitude? The amplitude, swing amplitude actually increases. With the same time constant, the settling distance gets higher as we make omega p and omega g separate. So that was why the settling performance was affected by the zero. Okay, before we move on to the nested Miller, um, on slide 17, upper right figure, y is omega 1 lower than omega 2. Y is omega 1 lower than omega 2. Omega 1 is, let me explain again. Omega 1 is just determined. Simply, you can think this is by uh, gain bandwidth product. GB, to use gain bandwidth product, GBW. This is just a gain bandwidth product. So, I mean, output current is GMV in, and the load is there. So unity gain frequency is not changing. Output impedance is just increased here because of boosting. So we have one pole. Until we meet this one, we don't have, pole. Even if there is a pole, we still have higher gain than, even if when the amplifier gain became unity, we still have this high gain and load cap. So the output impedance is just determined by the GM and 1 over, the capacitor's impedance. So it works like this.